Okay, this will be lecture 38 by Harvey Friedman, now on embedded maximality, please.
Yeah, so I did. I'm not quite ready to give this talk smoothly, but it's kind of. But I was tied up with preparation for a podcast. Uh, I think it's the series. It's called Theory of Everything, and so I had to do a certain amount of preparation for that, and also. Uh, I have made what I consider a very important expositional improvements on this embedded maximality, um, way more convincing than the last time. And but I think it's been a long time, so I think I definitely want to give this talk. But I'll be busy at work trying to finish this chapter up. This is going on for a long time. And I found out that there's some things about this. I think less is more in some ways. So we'll see and when I make these big, I call expositional breakthroughs, whatever, the idea is I am multiplying by a serious integer the number of general mathematicians who will sort of remember it or, you know, feel it. And this is the idea. Uh, and I think you'll probably agree that this is actually uh, it looks much more like a permanent subject than before. I mean, it always did look like that to some extent, but this is a matter of degree. And uh, I think the idea of spending, maybe 6 months, it could be many months if you look at it, rewriting this chapter, the positive part of this stuff is going to be well worth it. That's my opinion. But I'm hoping to get to the end, near the end of it. And next week I should have buttoned down a very large percentage of this chapter finally. I mean, a lot of it doesn't have to be reworked much. Now, the fortunate thing is that the reversal is always constant because everything that I do, even if I change, rewrite rewrite the positive part of the book, uh, it's always, the statement is always easily proved, easily implying the statement reversed. So the reversal does not have to be changed at all. Um, I mean, maybe the introduction to the reversal is changed to accommodate the context, but that's minor. So this book is called Embedded Maximality, and these are the chapters at the moment. This one being very constant. This one going to be heavily revisited right after we finish this one. Well, this one is what we're talking about. Now, this one is had a different title before, and this is where I look at piecewise linear and semi-algebraic. And there I don't have any maximality. This is embedded maximality without maximality. So I look at these embeddings, the embedding situation in the real point sets. And this, I think, is a very good introduction. This is a good way to ease the mathematicians in, because embeddings of real point sets is almost a subject that did exist or should have existed. I guess I have to use the AI to see whether or not there was traces of this. Of course, there's no incompleteness in this number two, of course. Uh, and this will have to be rewritten some with a new emphasis on the embeddings, because before it was written with invariants. And that won't require a lot of work because I think it's almost all liftable. And I might even be cutting out stuff, maybe, uh, possibly. So this actually uh, is going to be much closer to this. These two are going to be linked better now. Now that I'm doing embeddings, two and three are going to be linked better, and two is the one that's heavily mathematical, very standard mathematical. because it's piecewise linear and semi-algebraic and on the reals. All right, so we are talking about this, of course. This I have to really rethink. I had some original. Okay, there's a lot of more work to do to finish this book, but this is the big deal, the positive part of the book. Um, all right, so this chapter now uh, looks like this. This is not changed. This is not changed. This is uh, not changed at all, except that, this has been true 2 weeks ago. We're working only on the closed interval minus 1, 1 in this whole book now. The closed interval minus 1, 1, except of course the purely mathematical stuff is on the reals. But this is on the rationals between minus 1, 1 closed. Okay, so this is the new um, okay, well, no, this is not quite the new thing. Okay, but this is something that's been around. Uh, uh, it's changed because I talk about embeddings. I forget what exactly was 2 weeks ago. Probably not changed from there, but we'll go over it quickly. Um, this is not changed. So the big deal is uh, that the old work on the finite case uh, is goes through literally without any changes. I probably have to make some changes because I'm talking about embeddings. Some of the terminology may have to be uh, changed, but I think even the way I did embeddings, that was equivalent to the invariance in this context. So there's probably very little. There's a few words that need to be changed, but the point is, I have a complete solution to the usability problem for the finite case. That's the point, and it's all standard math. It's done in CFA, super exponential function arithmetic, because it uses Ramsey's theorem. The finite Ramsey's theorem is the only thing. Um, then um, then we start the serious stuff. I guess I call it beyond finite usability. Yeah, I think I like that title. So the idea is you have finite usability completely understood. You venture very, very, very little beyond finite usability. It's called outer extensions. You venture very, very little beyond finite usability, and you ask about these infinite functions, and you you're thrown right into more than ZFC, right? Thrown right into large cardinals. This is a very nice situation. This is what I always was aiming for. Now, the situation actually is even nicer. Um, First of all, the outer extensions are completely trivial definition, as you shall see. So, in asking whether their outer extensions are usable or not is impossible in ZFC. It's SRP stuff. So that's the punchline. But there's also a way of weakening this so that you're only looking at functions that fix an endpoint. You're looking at functions that fix at least one endpoint. The endpoints are two of them. They're minus 1 and 1, of course. If you make that simple restriction, that weakens the statement to just the functions that have uh, the ones that have that fix an endpoint. Then it drops down to Z. In other words, it drops down to aleph omega in strength. It drops down into con ZC. In fact, the point is that it becomes provable in ZFC, but not but you need infinitely many uncountable cardinals. I think it's a very nice situation. Uh, I make some variants, but you see, I keep this in a separate section. I make some variants so that I can state the results stronger, and the informative variants, so I can state the results stronger depending upon only the dimension k and the size of the finite part. You'll see what I mean when I get into the details. Um, but also there's some useful variants that are easier to that are easier to prove than the original ones that are actually easily shown to be equvalent to the original ones in here. And then this is constant. This has been around a long time, this stuff here. First of all, that everything is implicitly pi 0, 1 uh, over WKL. No, this has been around forever. And also the importance of that implicitly pi 0, 1 is very, very close to being falsifiable. Uh, they're equivalent, more or less. And falsifiability is important in science. You want That's what the whole point of experiments are. You want to you want to have the ability to falsify things, and then you say it doesn't get falsified, or sometimes it does, right? So okay, so and then I have these sections that prove okay, so it's called the outer extension usability theorem, OEU. And this is the case where dimension 1, and this is the case of dimension 2. So I've got it so that dimension 2 uh, is more or less possibly understandable by a non-logician, non-set theorist. Barely, but they got to be happy with the cardinal omega 1. So I think that's important. And I have a certain way of laying it out now that's getting good. Uh, there's another one where you fix the cardinality of the field to be 2, uh, and any dimension. This has been around for quite a while, but this is sort of restated a little bit. Uh, and then I just go right for the K and N version, where K is greater than or equal to 3 and N is greater than or equal to 2, because the other ones have been proved. And do this following the same way I did omega 1 up here, except that at some point you need a much stronger infinite combinatorics. It has to be much stronger, of course, because it uses subtle cardinals, the large cardinals. And then I do the weak one, because I had already done stuff like this. This weak one where it is provable in ZFC. This probably is. This is old notation here. Yeah, there is some joint usability that's important. In joint usability, you have several. Ah, yeah. In joint usability, you have several possible embeddings, several embeddings you want, and you're looking for a maximal chain that's simultaneously embedded by all these embeddings all at once. And this opens up a whole new can of worms, of which I open up only the little crack in the can to prove a basic joint usability theorem. Okay, we won't get to that today. Then I set it up how to actually, what is the actual formal results? Since I stated this informally using the word using. Everything can be shifted from maximal chains to graphs and emulators. The graph one I need to state because I need to show that the reversal applies. So we prove this statement. This is the new notation, slightly different. No, I think this is the same one as in the reversal chapter. Yeah. I think OISG is a little bit new, that for order invariance simple graph. That may be that four letters might be new, but so yeah, you can easily derive this from this stuff, all this stuff up here, like the outer extension usability theorem easily implies OSG SG max clique. And then, of course, that was reversed in now it's chapter 4. Okay, there's an infinite number of open problems. I mean, there's a vast array of difficult problems of every level of difficulty imaginable and reversal issues and so forth. Enough for, well, you hate to say this kind of thing, stick your neck out, but enough for the rest of the century, maybe. Okay, so this is never ch not changed. Basic background about order equivalence, order invariance, quantifier elimination for rationals with order. Okay, and then we have this. It's not changed. If you have maximality without invariance, maximality without invariance. Now we already did maximality without invariance in chapter 2, though we haven't talked about that for a long time, and that's in the purely mathematical context. But here we also have maximality without invariance. Uh, uh, like every order invariant relation has a maximal a chain, right? Just that. If it's order invariant. Okay, so we discussed that. This is old. A little bit of computational complexity stuff in here. Yeah, here. This is in general relations, and here it's in order invariant relations. Actually, this probably should be. This is stupid now. See, there's old versions of the book still in here. Uh, I said completeness issues. I think I meant computational complexity issues is in there. All right, now we get to the meat of stuff. We're starting to, not completely. So we put a condition on the maximal chain that it carries embeddings. So this double colon means partial map. So a partial map from A into B. Now here's the notion of embedding, in which we of course talked about it already, but let's review it. To be F embedded, so F is a one-dimensional object. To be F embedded means you're a partial map on our space. Is 1, 1. I looked up, the AI tells me that nobody does embeddings without assuming they're 1, 1, the word embedding. I actually don't need it. You can prove that if you don't have 1, 1 in here, you could actually prove that all the results about usability uh, hold. They're not changing. But anyways, I follow the AI advice. The definition of embedding includes 1, 1. Okay, and it means for all P1 through PK. P1 through PK is an S. It has to be in the domain of F. If and only if, when you apply the function, it stays in S. If and only if. So we say F is an embedding, or F, uh, actually, we also say S is F embedded. This is another way, another English phrase. S is F embedded. I put that in the final version. Now, here's the point. F is usable if and only if every order invariant relation on every minus 1, 1 to the K has an F embedded maximal chain. Yeah, and also F embedded. Needs to be defined there. Okay, so F is usable if and only if every order invariant relation on every minus 1, 1K has an F embedded maximal chain. And we proved in chapter 2, which we haven't talked about forever, that a lot of functions in math, piecewise linear and semi-algebraic, are F embedded. All those functions are F embedded. All of those functions are F embedded uh, uh, for various F, and various F are usable so I have to make up some other definition. So I have to do things like say, yeah, this might be an expositional issue. F is piecewise linear usable, or F is semi-algebraically usable, something like that, mathematical. And then say, look, we're going to drop the adjective and just call it usable because the thrust of this book is now chapter 3 and beyond. That's my excuse because I want to just keep usable. I don't want to put anything in front. Uh, Except I do K usable, but that's something else. So that's right. So in chapter 2 on the math, I'm going to have to say F is semi-algebraically, I'm going to have to put some adjective on the usability there. And then here, I won't have an adjective except this one here. Yeah. So I want to make it's better now. This day starts to look like a more consolidated joint subject here, heavily linked subject to regular math. This way of talking about this. All right. Trivially, if you have something usable and you cut it back, it's more usable. It's still usable. Or K usable. K usable just means we're fixing the dimension K. All right. So here is the embedded maximality program. Drum roll. Big drum roll, right? Here it is. To determine the usable F. Oh, I have a convention earlier. I forgot to emphasize. I put in a convention earlier that if I write F, G, or H lowercase, it always means a non-empty partial function from -1, 1 into -1, 1. It's always a non-empty partial function from -1, 1 to -1, 1. If I use little f, little g, or little h. Yeah. So that's a headline convention. And I remind the reader of that convention periodically. So the embedded maximality program is to determine the usable F. And to be usable, you have to be one of those Fs, of course. But the definition of usable was given earlier, right? Here it is. Just so you remember, right? Okay. So the embedded maximality program is to determine the usable F. We've completed the embedded maximality program for finite functions. This is a very nice situation. For finite functions, we understand it, and it's reasonably easy to state. This is carried out in full in section 3.5. The proof lies squarely in actually CIFA. I'm going to say something about CIFA in here. All right. The situation is radically different when we venture modestly beyond finite usability. In section 341, we establish usability for the most basic functions. Yeah, there's some trivial usability theorems that are just from finite Ramsey theorem. But to get the full thing is much more complicated. For the finite case, is much more complicated, but it's been done. All right. In another section, we completely determine which functions are one usable. There's a very nice characterization of the functions that are one usable. And one dimension is very different than two and higher. Then we do some abstract nonsense on the usable functions, closed under composition and this and whatever, in closed under composition and inverse, stuff like that. Uh, they're invariant under the notion of usability is invariant under isomorphisms. Isomorphisms that fix total isomorphisms that fix the endpoints. Um, Stuff like that is in there. Then we give two fundamental necessary conditions for usability. Um, One is strictly increasing, and the second is more involved, but it looks like this, if you remember, my four fingers are wiggling. This goes to up to this. This is an endpoint, and this is an endpoint, and we go up and up this way. We want to make sure that it never happens. Uh, all right, so maybe okay. I told you about this convention. Yeah, so I'm happy with putting it here because I said that the program was to determine the usable, and usable has these things in it. Yeah, so here's the convention, right? All right, so the most basic usability is when we just have if every strictly finite function from that stays away from the endpoints is usable. This is from Ramsey's theorem. See, usability is a friendly thing. And usability gives us large cardinals very quickly. Now, this argument means that we need to know that we stay away from the endpoints. And uh, uh, if you fix the endpoints, that's about as good as being inside this thing. So you get this also from the Ramsey theorem. It's actually a stronger thing holds, but they've just fixed some endpoint, but that's much harder, and that's in the section on finite stuff. With one usability, we have this elementary thing that since we're in one dimension, we want to figure out what the uh, uh, relations are on minus one to the 1th to the first power. So what are the binary? So what are the binary? What are the order invariant binary relations on minus 1, 1? And there's 8 of them. And the maximal chains are easy to compute. They're either the singletons or the empty set or the whole space. So F is one usable if and only if either the field is not everything or the function has a fixed point. So just about any reasonable function, just about any reasonable function is one usable. Obviously, there are ones that are not. All right. And then we have a bunch of general nonsense about inverses and compositions and usability and K usability. Oh, and the minus function. So the reversals. Yeah. I mean by reversal, be reversing an order. Uh, in other words, there is this anti-isomorphism that maps minus 1, 1 to minus 1, 1 called minus, the minus function. And then this operates on functions. And then you have this also is friendly with usability. Here we go. Here we are. Get this. Finally, this. Yeah. And then we have the necessary conditions. Yeah. Extremely important is that strictly increasing is necessary for usability. For two usability and higher. Sorry. It's not necessary for one usability. It is necessary for two usability and higher. Like here. And then this is the other necessary condition that's a little more involved. we want to say that we don't want we don't want this configuration, this or the other. We don't want these configurations. I always wonder if I have this stated right. It doesn't look like. Uh, I think I stated this wrong. Uh, it's this and the minus of it. It's this and the other one. Minus one is less than f of minus one, and and one goes back to yeah, and that goes back to that. That's fine. And the other one is uh, I probably should have just done this. Yeah, I should have just done that. Uh, F inverse of one, yeah. Can't be greater than one. What is going on here? Uh, um, one is all right. Let me not waste our time with this. I just have to fix this up. This is supposed to be the dual of this. Didn't write it down right. All right. So and we have a hierarchy here. K plus one usable implies K usable. Yeah. And then we have this giant section on finite usability that hasn't been changed really. All right. Now we get to the heart of the matter. Here, beyond finite usability. Okay, I remind you of this convention that this is non-empty partial functions. And with my wiggle room. Okay, so outer extension usability. We find that once we very modestly go beyond finite usability, we run squarely into ZFC incompleteness. A particularly basic extension of non-empty finite F. Well, we now have just F, finite F, because of our convention. Extension of finite F are its outer extensions. The outer extension of F extends F by the identity on all rationals that are either entirely below or entirely above the field of F. Okay. So here's a function that does, finite function that does some stuff here. And then we want to go out, and make it the identity there. Okay. All right. An example, suppose F is the function of cardinality one. It just maps one half to one half, minus one half to one half. The outer extension is F union the set of all PP such that P is between 0 and minus a half, or P is between a half and one. All right. More formally, if let F be finite, the outer extension out of F is the extension of F by the identity on max of the field to 1, union minus 1 to min of the field. And because F is a non-empty function, max and min of the field of F exist. That's why I like to stay away from the empty function. I think it's simpler just to have this. So that's the outer extension. You're fooling around here, and then you make it the identity up here. Of course, if you're fooling around here and actually minus one and one are both in the field, then the outer extension of F is the same as F. So, you see, but you may not, you may be all inside here, and then you're going to do this, or maybe you're inside here and you go all the way to one over here, then you're only going to make the outer extension on the left side, whatever. Right. So this is okay. The whole book is basically is surrounding only outer extensions and maybe a variant. Yeah, just outer extensions. The book is nothing but outer extensions. You can extend by the identity where you go in between, inside, and even stay strictly increasing. That's what I used to do. Last lecture, I was biting off more than I could chew. And I think you get a lot of usability. I know that a lot of those cases, maybe, but that's beyond the scope of this book now. Less is more. That's part of the exciting new ventures in the last section, is to study what happens when you don't do an outer extension, but you do a lesser extension. And the extension I'm talking about is where you only add the identity only add an identity. And it can be shown that, and I will remark this there, it can be shown that in general, if you have to keep strictly increasing, that when you do this, basically this is the same as considering all order invariant embeddings, all order, or not order invariant, all order theoretic embeddings, all the ones that are definable with less than. So things are going to fit together, but then it gets quite involved, proving usability. And I think I overstated some things I can't do. Today I'm not overstating things. Less is more. But I think there's a lot of open questions and a lot of difficulties in actually seeing what is usable, even for these very simple extensions by identity. Extensions by identity. Of course, there's a whole vista of further things where you're looking at piecewise linear embeddings, partial piecewise linear embeddings, or higher, even more partial semi-algebraic embeddings. And there, I haven't even begun to think about it. And there, things are probably yet more delicate and difficult and interesting and rich. Okay, but so we're doing very minimalistic things here. All right. The proof uses large cardinals of the outer extension usability theorem. If f is finite and usable, then out of f is usable. And this is a very nicely stated theorem, given the fact that the finite case has been completely and totally solved. And if f is finite and usable, then the out of f is usable. And out of f is, very specific, simple notion. It just means I'm extending f by the identity strictly above and below its field. Okay. So this is my rollout. This is my rollout. Now, weak outer extension usability theorem says if f is finite, fixes an endpoint, either -1 or 1, and strictly increasing, then the outer extension of f is usable. This turns out to be easily seen to be a weaker theorem, and it can be proved in ZC. Using Erdős-Radó in a way that I already did present to you many months ago. So I can reuse old material with Erdős-Radó. So that's called weak outer extension usability. So now we, on the informative side, we want to put some parameters down. I already did. I think we already talked about K usability. Okay, but okay, so here is the full order, and here is the OEU, um, outer extension and usability theorem, parameterized by the dimension K and the size of the given function, of the given finite function. Uh, actually, this is remnant of something I got rid of just before we talked. Yeah, I had this a little different setup that was actually not really right. And this is what I meant to say, which is better anyways. So if the cardinality of the field is at most n and usable, and f is usable, then the outer extension of f is k usable, right? So that's what this means. Uh, and then k star just means for every n, this is true. And that's just fixing uh, the dimension. That's all that means. Now here's where you fix just the size of the function. We fix the size of the field of the function is star n with all quantifying over to all dimensions n, all dimensions k. Okay, and now the weak one. Also, we work with the weak one like this, parameterizing that in the same way, fixes an endpoint is strictly increasing. Then the outer extension is k usable, right? Now, when we actually get down to brass tacks and prove these things, we want to normalize, we want to make things a little bit more normalized. And then this is equivalent. So for OEU, we have the statement that, and this F is already given this way. So this is, see, I didn't really have time enough to polish this lecture with too many things going on, including thinking of this lecture, of these things, because that's the convention. Okay, if F is finite and strictly increasing, then out of F is usable. Um, Now wait a minute. No, that's the one that's false. This is false. Uh, so what was I meaning? Ah, yes. This is the one with okay, this is the one with fixes an endpoint. No, yeah, I don't want to. Yeah, okay, so I have to, I'm not sure what let's see, just let me think for a second here. I already have, um, I think I remember what I need to do here. Uh, if F, yeah, this is it. This is what I wanted to say. Yeah, this version. If F is strictly increasing, then out of F is usable. And if F, partial, of course. All right, let's see if we can make sense of this here. If F, oh, I think no, this is right. I have to change this. This belongs down here. Yeah, something happened here. Somehow it's down here. Okay, so if F goes from 0, 1 to 0, 1, there we are. Okay. I think I erased something here. There. Cardinal, the field of F is at most, come on. All right. So the thing we actually prove is this, that if I have a partial function if I have a partial function of a finite partial function from here to here, and it's strictly increasing, then out of F is usable. This is equivalent to the original neater OEU, which is if F is finite and usable, then out of F is usable. All right. And then this is the same thing with a bound on the size of this, and this is the same. Okay. And then you have equivalence of everything. These are all equivalent. We talked about this. We don't have to go over this. This is easily proved from this characterization of one usability. And I'll go through, the last thing I'll do today is talk about the proof, at least for the 2 dimensions. And again, it's similar to what it is before, but it's better organized. It has to be done for this new setup. We let F be finite, strictly increasing and mapping here into here, right? That's what this is the version OEU prime. We show F is usable, 2 usable using omega 1, right? That's what this is about. And we can assume that F is not just cardinality 1 function. The domain has at least 2 elements, because otherwise we wind up at trivialities. We can normalize F using isomorphisms. So we can normalize it so the field of F is either is either exactly 0n, 0 divided by n to n divided by n, or it's 0 over 2n all the way to n over 2n. In other words, it doesn't go all the way up to 1. Those two cases actually have to be distinguished because the outer extensions are so different. In the first case, the outer extension uh, goes all the way up to 1 as a non-fixed point. And in the second case, of course, it goes up to 1 because it's the identity on 1, but it's got its last non-fixed point lower, and I make it normalize it to be a half. Yeah, this is a little bit because I changed some things just before I came here, before the talk. All right, so we work on this case. We work on this case, and then we just remark in the last section how we modify the proof in that case to handle this case. See, that's how I do it. I don't want to handle them both at the same time. I try to do that, and it expositionally gets a little nasty. And so we go to the transfinite, and we have this is the space we work on. Omega 1 cross the rationals from 0, 1 with its usual order, union this singular point minus omega 1, 0. And we put 3 orderings on there. This is a dense linear ordering with left and right endpoints on W. This is a well ordering on W. And this is the well ordering lifted to W squared. And so we define all this stuff. I know that this J no longer is important. All right. So we've been through this kind of thing. I'm mixing the cases that I wanted to knock off. Yeah. So anyways. Okay. All right. We got this space, this transfinite space, and we have the relation on this space. We lift the order invariant relation canonically on this space. We actually get a maximal chain in our star that's embedded by a special transfinite embedding we're going to talk about. So, and this just means I'm lifting all my notions canonically to the transfinite. That's all that is. That's nothing. So we have this well ordering less than double star, and then we make our beloved inductive chain by transfinite recursion. We build it by transfinite recursion. It's read the inductive chain, ICH. And this is in the transfinite. And then we find a sequence of omega limit ordinals by some large cardinal, by not large cardinals, by some countable, some combinatorics of omega 1. We get this. I'm not going to go, because it's almost 11, I'm not going to go much into this, but we build an infinite, we build by model theoret by standard model theoretic combinatorics, uh, where's this set E? Just a second. Yeah, here. We get a closed unbounded set in omega 1 that interacts in an important way with ICH of R star. Uh, and we've done this many times. We This is a closed unbounded set, and it has uh, the right kind of properties that are sort of like go back to Gödel's collapsing lemma. Uh, we form an elementary chain, and we understand the inductive chain better. That it has some symmetries, and then you can use that to use uh, to get the indiscernibility that we need for the embedding. So actually, we get that this a chain cut back is an out of F star embedded maximal R star chain. In other words, we get the embedding that we like uh, by making the finite part uh, imitate, making the finite part that was in the rationals originally, making the finite part work on the indiscernibles. Remember, this finite part is a nice discrete thing. Just work on the indiscernibles because the indiscernibles of cardinality that we're using are the same cardinality as the field of F. And if we do that, it will be an embedding because of the large cardinal comment, because of the combinatorics, it will be an embedding. So we have the embedding, we have exactly what we want, except it's in the transfinite. And so the last steps are we go to a countable elementary substructure, which means that we can assume that we're really on -1, closed with a dense linear ordering. We go to a countable elementary substructure and argue that that's isomorphic to a system like this, where F is our original F, but S is some k-dimensional set. And then we argue that S has to be an F invariant maximal chain in R because that's what happened in the transfinite. So I think that this can be made very clear. And then when you lift it to a higher dimension, the large cardinal combinatorics that needs to be plugged in will be quite clear. That's the way it's set up. And then there's Erdős-Radó theorem is needed if you want to do the weaker one. The Erdős-Radó theorem is enough large cardinal combinatorics. You don't need the large cardinal combinatorics. The Erdős-Radó stuff is enough with the Beth ends. Beth omega, Beth, yeah. Well, you know what I'm talking about. 2 to the 2 to the 2 to the Aleph naught. With that stuff to get the indiscernibles that you need to carry out the same argument. The idea is that there's just one argument where the cardinal combinatorics is adjusted accordingly. Okay, so everything will be cleaned up and understood next time, unless I get an idea to make this even more transparent for the mathematicians. But I think that I'm pretty much done with that, with 4 tries or whatever it was. That I think this is getting into a very advanced state, well controlled and everything else. So I now turn the floor over to Andreas.